So in the last section, we looked at surfaces and then we used Green's theorem to change from a line integral to a double integral, and we computed flux. Well, now we're going to use that same idea using Stokes' theorem. And Stokes' theorem is actually a form of Green's theorem. So we're going to use Stokes' theorem to compute circulation across a surface. So that would be in three-dimensional space. So when you think about a surface, there's going to be two normal, and here I'm talking about unit normal vectors at every point on a surface. One will point outward and one will point inward. So something we have to be careful of when we're using Stokes' theorem is that we have to choose the correct normal vector that's consistent with the orientation of our surface. First, what I'd like to do is show you where our circulation formula comes from. Going back to our region in two-dimensional space, we have a curve that defines, and here our curve is oriented, that's going to define some region. Now at every point in that region, since this region is in the xy plane, I can find a vector orthogonal at any point in that region that's going to be parallel to the z-axis. So let's just look at that as being some vector parallel to the k vector, which is 0, 0, 1. Recall that when we were looking at circulation, our curl, or our integrand over our region, was the partial derivative of g with respect to x minus the partial derivative of f with respect to y. And that was a dA. Remember that that's what this line integral f dotted dr was equal to, which means this integrand, which is a cross product of the delta cross f dotted with k, that's actually our curl. And since k is simply going to be 0, 0, 1, then our curl is simply delta cross f. So these integrals are all the same. Now we're going to go from a flat plane to a rounded surface. But everywhere on that surface, we're still going to have a normal vector, unit normal vector, and it can point outward or inward. We have to remember that this vector is going to be consistent with the way that our curve is generated. So all we do is replace this vector k with a normal vector, and we've changed from a two-dimensional flat surface to a three-dimensional surface in three-dimensional space. So notice that it still corresponds to that same line integral, but now it's going to be delta cross f dotted with our normal vector. So how do you know which normal vector to choose? That goes back to the right-hand rule. So if you take your right hand and you curl your fingers in the direction that the curve is generated, then the direction that your thumb is pointed in is the direction of the normal vector that you're going to use. So that's Stokes' theorem, and that's how you would compute circulation in three-dimensional space, which brings us to this box that we have below. Oh, we're going to go from a line integral, as we did previously with the flux, to a surface integral. So line integral, you integrate about a curve. A surface integral, you integrate with respect to a surface. But remember, we can also use what we had previously. that we could take our vector field and we can dot it with r prime of t dt, because these are actually the same. So don't forget, you can use stuff from 16.6. All right, just some properties that are going to remain consistent is that let's say that f is a conservative vector field. Then there will be a potential function phi, so that f is going to be the gradient field of phi. And if it is conservative, that just means the cross product is going to be the zero vector. Example 1, we're going to use Stokes' theorem for the vector field x, y, z. S is the paraboloid 8 minus x squared minus y squared. Z values are going to go from 0 to 8. C is the circle x squared plus y squared equal to 8. And it's oriented counterclockwise. So it's oriented in the usual direction. So the first thing I'm going to do is compute delta cross F and ignore those roosters. And I'm going to leave off the I, J, K and be lazy. Remember, our del operator is a partial with respect to x, partial with respect to y, partial with respect to z, and F is x, y, z. So it looks like that is going to be 0, 0, 0. That's nice. When I compute my integral, it's going to be the 0 vector dotted with the normal vector. And that's just 0. So I didn't even have to figure out what the normal vector was, since my integrand was 0. Remember what that means. Although it's not in this question, that just means there's no circulation. We're going to do a few more examples, and something to keep in mind is remember that you can always use integrals from prior sections. You don't have to just use the integrals, the line and the surface integrals in this section here. Example 2, we want to evaluate the line integral by evaluating the surface integral in Stokes' theorem. So all that's saying is that use the double integral over the surface of the cross dotted with the normal vector with an appropriate choice of s. Okay, so the difficulty here is my vector field f is given, so that's not a problem. Finding n and being able to describe s. So remember, we can always use r instead. Over dA. We're allowed to do that. So I have my vector field. C is the boundary of this plane z equal to 4 minus x minus y. I have no problem figuring out the cross between delta and f, not a big deal. N is going to be an issue. So one thing you could recall is that when you have an explicit function z, normal vector would be plus or minus negative partial of z with respect to x, partial of z with respect to y, 1. And if you don't remember that, you can always just write this in the normal form x plus y plus z equal to 4, and recall that the normal vector would be the 1, 1, 1. But remember, the direction does matter when we're using Stokes' theorem. So we would choose either the positive or the negative 1, 1, 1. So again, that's just the coefficients on x, y, and z. All right, so let's go ahead and I'm going to go ahead and sketch this. You don't have to, I just prefer it. Sometimes it's hard for me to see which normal vector I would choose. So these all intersect the axes at 4. And since this is my curve, and orientation is clockwise, got to be careful because that's not the usual way our curves are generated. Since it's clockwise, it's going to go around this way. I'm going to add some arrows in. Okay, so if you take your right hand and you hold it up to that graph and you try to curl your fingers in the way that that curve is generated, it's very difficult. So you've got to turn your hand so your thumb is facing downward. And then you can curl your fingers of your right hand so that it goes in the same direction of the curve. And you can see the direction that your thumb is pointing in. It's pointing inward to the origin. So we're going to be taking the down or the inward vectors, which would mean I'm going to choose my n to be the -1, -1, -1. +1, +1, +1 would give me an outward vector. Next, what I'm going to do is I'm going to compute the cross. And I'm going to be lazy again and leave off the ijk. So my partial derivative with respect to x, y, and z would be x squared minus z squared, y, and 2xz. Looks like that's going to be 0 minus 2z plus 2z minus 4z and 0. So I have n, I have f. The only problem with my integral is I don't know how to describe this surface. But I do have my vectors, and I can dot them now if I wish. I'm not going to, though. All right, so I could just use the region instead. Let me go ahead and look at how we have previously defined these types of integrals, going back to our usual double integrals. Remember that if we let z equal to 0 and we look at the region R in the xy plane, and let me draw that again, we can just go ahead and integrate with respect to this region. I could let my x values go from 0 to 4. And now my y values, I have to be careful because I can start at 0, but then the largest y value would be on that line, which is y minus x. So y values would go from 0 to y minus x. This integral then becomes, I'll put the x on the outside because it's constant, y on the inside. And then if I were to look at this dot product, I can't use z because I'm integrating with respect to x and y. So I have to replace z with 4 minus x minus y. Maybe it would have been better if I went ahead and did the dot product first before substituting for z. And this would be dy dx. Now it's just about the algebra. If we go ahead and look at this, would be what? Negative becomes 16 minus 4x minus 4y, I believe. Oops, why am I writing this? I'm writing my integration, limits of integration wrong. 4 minus x, 4 minus x. So 16 minus 4x minus 4y dy dx. And let's see if I have enough space here. We have 16y minus 4xy minus 2y squared. And I keep forgetting stuff. Trying to do algebra in my head while I write and talk at the same time. This is 16 4 minus x minus 4x times 4 minus x minus 2 4 minus x squared. And then you could simply multiply everything through combine like terms and so on. I'm going to pull out a 2. But I'm going to be lazy. I can see that I can factor out a 4 minus x from all these terms to get 6, 2. No, took out a 2 to get 8 minus 2x minus 4 minus x. Okay, so getting rid of parentheses and combining all that stuff, I think it is 16 minus 8x plus x squared. Again, double check me on this, you guys. Okay. So integrating, I get 16x minus 4x squared plus x to the third over 3. And then I think I'm just going to plug this in a calculator and use my fraction key. So 128 over 3 is what I have. Remember what we're doing, we're computing circulation. So in this case, we have a positive circulation. In this last example, example 3, we're going to use Stokes' theorem to evaluate the surface integral. We're going to assume that n points in the positive z direction. We have our vector field F. S is going to be the upper half of this ellipsoid, z squared equal to 1 minus x squared over 4 minus y squared. Again, I am going to go ahead and do a little sketch. Let's say if z is 0, then in the x and the y, it's going to be sort of oblong. Sad sketch. And then my z super crooked. All right, so this is 2 and this is 3. I'm going to go ahead and sketch if z is equal to 0. I'm just going to do a sketch in the xy plane so I'm make sure I did this correctly. So x goes 2, y goes 3. Yeah. Okay. So we have this curve, and I don't know the direction it's generated in. So the curve here that we're talking about, remember the curve is the curve in the xy plane. So that would be the base of this ellipsoid. I know that since we're pointing, the normal vectors are pointing in the positive z direction, so these are our normal vectors, that the curve is going to be it's going to have to be generated counterclockwise. All right, so I got all that stuff down. Let's go ahead and see if we can define the curve. So I think what I'm going to use, because it's going to be hard for me to find my normal vector, I think what I'm going to use is over a region to do f dotted with r prime of t. Since I know I can define the curve in terms of r of t, which is going to be an ellipse. So that's going to be the x value would be 2 cosine of t, y would be 3 sine t. And if I want, I can put a z value, since I'm in three-dimensional space, of simply r. The t values are going to go all the way around, so 0 to 2 pi. And I think that would be easier for me to work with. I'm going to look at this line integral over the curve. Which is going to be the integral from 0 to 2 pi. My vector field f, written in terms of t, would be 2 cosine of t, 3 sine t. And I don't really need the 0 because when I dot it with the derivative of r, which would be the negative 2 sine t, 3 cosine t, since I got a 0 here as well, they'll kind of cancel each other out, dt. Let's see, when we do our dot product, I have a negative 4 sine cosine and a plus 9 sine cosine, which gives me 5 sine cosine of t dt. And I could simply do a u substitution on maybe the sine or the cosine, it doesn't really matter. Or I can use a trig identity, because I don't feel like changing my limits of integration, of rewriting 5 sine cosine as 5 over 2 sine of 2t. Is that correct? Sine of 2t is 2 sine cosine. The 2's cancel. Yes, it is. And I derive the sine, negative cosine of 2t divided by 2 would be a negative 5 over 4 cosine of 2t. And that would simply be 0. So again, no circulation, although it wasn't asked. So we're done with our examples. Just keep in mind that you're not restricted to just using the line and surface integrals in this section when you're using Stokes' theorem, because the double integral over the surface integral, is equal to that line integral. We can use line integrals from previous sections, like the vector field dotted with RDT. The question does come up, though, that are the properties still the same when we talk about curl and circulation as it was when we were in a two-dimensional region? The answer is yes, pretty much the same. Something that I did want to emphasize is that when we talk about curl, we're looking at the cross of the delta operator with our vector field. So that is the curl, because remember what we did in the beginning is we took the curl, which was the partial derivative of g with respect to x minus the partial derivative of f with respect to y. right? And we replace that with this cross product. So this is the curl. If the curl is a zero vector, that means your vector field is conservative, which means that the integral, if the curl is zero, then the circulation is going to be zero as well. Okay, again, we're in three-dimensional space. Something else is the same is circulation is work. If the vector field is conservative, no work is done. We also computed average values, so we can compute average circulation. Just compute the integral, the surface integral, and divide by the surface area, or compute the line integral and divide by the surface area. Previously, when we talked about circulation, we also talked about a general rotation field. Still the same here. So if you take a rotation field and you write it as A cross R, A is going to be a constant vector that's non-zero. R is going to be the vector XYZ. Then when we talk about the circulation or the rotation, it's going to be in the direction of our vector A. And we had talked about angular speed previously. Still the same, still the magnitude of A. Well, since our curl here, the cross product is actually del cross A cross R, then recall previously that would be 2 times the vector A. Here there's a typo. It shouldn't have the is constant. That shouldn't be there. It's just 2 times the vector A. If we are in a general rotation field, then computing average circulation is actually very easy. Instead of computing that whole integral, you just have to compute 2 times the magnitude of A times cosine of theta. So the question is, where did this theta come from? Well, this is actually the formal definition for a dot product. And here we're looking at our normal vector dotted with A. So theta is going to be the angle between them. Something that may come up in maybe your physics class. Well, let's say that we have a curve, some oriented curve. And it's defining two surfaces where you have an inner surface and you have an outer surface. They have the property that their normal vectors are going in the same direction. So it doesn't matter where I go on the inner, I have a parallel normal vector on the outer surface. If this is the case, then to figure out circulation, you only have to compute the integral for one of these surfaces. So the S sub 1 integral is going to be equal to the S sub 2 integral. However, you got to be careful. Let's say that you have a curve. So we have this oriented curve. And you have surfaces below and above the curve. Well, in that situation, since if you look at this diagram, the surface below is not being generated in the same direction as the curve, so the normal vector for the lower would be inward facing. And the normal vector for the upper is going to be an outward facing normal vector. So you'd have these types of normal vectors. What's going to happen is when you compute the circulation for the bottom piece and you add it to the circulation for the upper piece, they're going to cancel each other out because one is a negative, one is a positive. If you have this situation, circulation is simply 0. So those are just some properties that go with circulation and curl in three-dimensional space, and that's it for this section.